Okay, so for our final unit, we're going to talk about simple harmonic motion. Okay, so this is actually a pretty important area of physics. Now, we're hitting just the basic surface of it, um, but if you were taking more advanced classes in physics, almost everything that vibrates can follow a simple harmonic pattern, and so that's why it's important to get these basics out of the way. So first we define simple harmonic motion as simply motion that is periodic or repetitive. Okay, so if you imagine two scenarios, so I'm going to create two position graphs that follow that sort of idea, is that they're periodic. So imagine like a wave graph. So this would be a particle that bounces back and forth. And then imagine like a step graph. Okay, so both of these graphs are considered periodic because they repeat themselves. Okay, so that's what we mean when we say that the motion of something is periodic. Now, to make it simple harmonic, we're looking for graphs that have a position graph that is more sinusoidal, like the first one. Okay, so to define these graphs, when you draw them out, there's an equilibrium line that cuts through the middle of the graphs. Okay, and so if the motion of the object kind of bounces back and forth over this equilibrium line, we refer to it as periodic motion. Okay, so remember, a period is the time it takes for one full cycle to occur. So on both of these graphs, you can see that a cycle begins at one point, and then when we reach that point again on the graph, that's considered one cycle. Okay, so once you've reached one period and the motion begins to repeat the same process, that's how you know you have periodic motion. So for our purposes and just in general, the first graph being sinusoidal, this is more representation of what an actual simple harmonic oscillator looks like. Okay, so to get an idea on how these graphs are produced, okay, we're going to look at a little visual example. Okay, so in this example, you're going to have a mass that's hanging on a string, and then as this mass is oscillating up and down, you see how its motion kind of matches that of a sine curve. Okay, so that's what we mean when we're talking about simple harmonic oscillators or simple harmonic motion. So if we look at the graph, there's a few properties of the graph that I want to identify. The first is, if the graph is centered along an equilibrium line, then the highest point that it reaches from that equilibrium line is known as your amplitude. And it's going to be the same value on the other side of that equilibrium line. Okay, we've already said that the period is the time it takes to complete one cycle. Okay, so we mark a point on the graph, and then we just have to mark a very similar point in the next cycle. Okay, now one of the other things you can see from this is something we refer to as frequency. And so frequency is simply the number of cycles that occur per second. Okay, and we can develop a relationship for this where frequency f is simply the inverse of the period, so just 1 over the period. Okay, and in terms of the units, since 1 over period would be 1 over seconds, this term is referred to as hertz. So it's labeled with just an HZ. Okay, and so this describes what some of the main properties for a simple harmonic oscillator. Okay, and one of the other property terms you're going to see is something we refer to as the angular frequency. Okay, now you might have seen something like this already, okay, because if frequency represents the number of cycles per second, angular frequency refers to the number of radians per second. Again, you've seen this already because this is essentially what angular velocity is. So it's not much different than angular velocity, but we're not talking about things going in circles, so we don't refer to it as angular velocity. When you're referring to an oscillator, we're referring to it as angular frequency. Okay, so to simply calculate the angular frequency, it would just be taking 2 pi times the regular frequency, and then since frequency is the inverse of period, we can also express this as 2 pi over the period. Okay, so you're going to see this term pop up a lot as we do this simple harmonic motion unit. Okay, it helps to clean up our terms, it helps to make the equations look neater, but you do need to make sure you understand the difference that in this case the omega does not represent angular velocity, it represents angular frequency. Okay, and so other than knowing the type of motions you're in, there's really not much difference between what those two variables do for us. Okay, so in studying the motion of things, we're going to look at the motion of a simple harmonic oscillator. Okay, and so you can read the book for the development of these equations, but it basically starts off with that the position function is expressed as the amplitude of our oscillator times the cosine of the angular frequency times time. Okay, and we're going to build on this a little bit further in the next video, but for right now, this is enough for us to know something about how the oscillator moves. And if, depending on what you're given in the problem, you don't have to have this in terms of angular frequency. You could replace that with 2 pi over the period times time, or you could have it as 2 pi times the normal frequency times the time. Okay, so this equation will tell us the position of an oscillator as a function of time. Okay, again, it's assuming some initial conditions that I don't want to get too far into right now. We'll do that in the next video. So if we start with a graph of an oscillator, okay, we've got a position time graph of an oscillator. If we look at some of the key points on that oscillator, like for example these points where the slopes are 0, we know that the slope of a position time graph is the velocity. So on this oscillator, this is telling us that when the object has reached a position equal to the amplitude, then the velocity of the oscillator will be 0. And that should make sense because if something's bouncing back and forth, when it reaches the furthest point away, it's going to stop before it starts getting pulled back the other way. Okay? Now, at the same time, if you look at the points where the graph crosses the x, or the time axis, okay, if we look at those slopes represent the maximum slopes before it starts to turn and go back to 0 in terms of slopes. So that means when an object is at its equilibrium position, the slopes are at their maximum values, which means the velocity of the oscillator is also at maximum. Okay, so in terms of how we develop an equation for the velocity, we would do that in just the standard way we've always created the velocity equation. Okay, you want to start with the position equation. Okay, and then we know that to find velocity, you have to take the time derivative of the position. So if we're going to take the derivative of this function, okay, so you'll have to remember how to take derivatives of trig. So remember the property, and also chain rule. So the derivative of cosine is negative sine, but then because of the chain rule, the term next to the t inside the cosine function is going to come out. So you end up with the velocity expression is the negative of the amplitude times the angular frequency times the sine of the angular frequency times time. And so this would give us a velocity expression. Now to understand the maximum velocity, in terms of the equation, sine or cosine max out at values of negative or positive 1. Okay, so this means that the maximum velocity occurs when sine is equal to positive negative 1, which makes that equation either a plus or minus amplitude times the angular frequency. Okay, so and that's a pretty standard property for an oscillator. The maximum speed is the product of its amplitude times its angular frequency. Okay, and we're going to elaborate on a lot more of these variables as we go through this. Okay, so this also tells us that, when you see the plus or minus, the maximum velocity will be a positive number when the object passes the equilibrium on its way to the positive amplitude. And then likewise, if it's negative, that must mean the object is on its way towards the negative amplitude. Okay, so another important thing for us to cover is energy within an oscillator. Okay, because just like everything, before we get into the dynamics with forces and things like that, it's good to kind of see this holistically in terms of how much energy is in an oscillator. Okay, so consider a mass that's attached to a spring, and we'll make this horizontal and assume that the surface that the box or the object's touching is frictionless. Okay, so if this box is brought out some distance from equilibrium, okay, for this case we'll just call it x. Okay, at this point it has some amount of energy. Now this might not be us grabbing it and moving it, this could be the box just moving on its own and bouncing back and forth. Okay, but when it's at a position x, if we look at the forces acting on it, you have a normal force, you have its weight, but since there's no friction, those two aren't really going to matter here. But you do have a spring force that's trying to tug it back at all times. Okay, recall that the spring force from Hooke's law is the negative of the spring constant times its displacement from equilibrium. And remember, it's negative because it's always trying to restore it back to equilibrium. Okay, the potential energy for a spring, remember, is 1/2 of the spring constant times its displacement from equilibrium squared. So if we're trying to find the total energy in an oscillator, it's the total mechanical energy, so we're going to do the kinetic, 1/2 mv squared, plus the potential, 1/2 spring constant times the displacement squared. Now, if you imagine what happens if you get out to the amplitude, okay, just to kind of help us give us some numbers that we know. Okay, we talked about this based on the graph that when you go out to the amplitude, we know that the object stops. So that means at x equals a, the velocity will be 0. And since total energy in this system is constant, we can use that to help develop some understanding of how much total energy is always in an oscillator. Okay, so when you're at the amplitude, your velocity is 0. So if we plug that into our energy equation, okay, we get 1/2 times the mass times 0 squared plus 1/2 times the spring constant times the amplitude squared, which means that the total energy in an oscillator is equal to 1/2 of the spring constant times its amplitude squared. And that's a constant term for an oscillator. If you know its spring constant and you know its amplitude, you know how much total energy you have in that oscillator. Okay? Now, what if we look at it the other way? What if we are passing through equilibrium and we've reached our maximum speed? Now, we mentioned earlier that the maximum speed is the amplitude times the angular frequency. But what happens if we look at this in terms of energy? Okay, so we do the same thing. We know it reaches maximum velocity when you're at equilibrium, so at x equals 0. Okay, so let's set up our mechanical energy equation. So total mechanical energy is the sum of your kinetic and potential. So the kinetic, 1/2 mass times the maximum velocity squared, plus the potential, 1/2 the spring constant times the displacement, which is 0 because you're at equilibrium. So our only energy then is in the form of kinetic. But we discovered on the previous slide that the total energy is half of the spring constant times the amplitude squared. And since it's constant, that means our kinetic must equal this total energy. So if we do some algebra, we see the halves go away. And if I divide off the m, okay, we get this expression that the square of the maximum velocity is equal to the spring constant over the mass times the amplitude squared. And so if I take the square root, that means the maximum velocity is the square root of the spring constant over the mass times the amplitude. Okay, and so this gives us a little more detailed understanding of how to find the maximum speed. But if we take this and know that we're talking about the same oscillator, and we already discovered that the maximum speed is the amplitude times the angular frequency, well, if we set these equal to each other, because we are talking about the same oscillator, therefore we're talking about the same maximum speed, we see that if we cancel out the amplitudes, then this expression of the square root of the spring constant divided by mass is really an expression for our angular frequency. Okay? And that's a very interesting result, because that tells us that as long as we know the mass of the oscillator and how much spring constant is on that mass, we can already determine what its angular frequency is going to be. Okay, and so there's a couple other interesting results that come from this. Okay, if you recall the period equation, or if you look back at what angular frequency was, it was 2 pi over period. So if I solve it for the period, it becomes 2 pi over angular frequency. And if we plug in the result we just got, angular frequency is square root k over m, we end up with an expression that the period is equal to 2 pi square root mass over the spring constant. Okay, and so this is an interesting result because it tells us that the period of the oscillator does not depend on the amplitude, which is a little counterintuitive. So if I take the mass and I only pull it out a little bit and let it go, it would have the same period if I were to take the mass and pull it out twice as far or 3 times as far or however far I want. It would have the exact same period. The amplitude does not affect the period of the oscillator. Okay, and then we can also then calculate frequency, because frequency is 1 over the period, and since we have this expression for period now, the frequency of the oscillator becomes 1 over 2 pi times the square root of spring constant over the mass. So these are just some interesting results to get us started, and the next video we'll do a little bit more of the dynamics and understanding some of the origins of where simple harmonic motion gets these equations from.